Students, in the previous lecture, we have discussed potential energy due to a system of 2-point charges and potential due to a continuous charge distribution. In this lecture, we will study potential energy of a dipole in a uniform electric field. So let's take an uniform electric field. Suppose here parallel lines indicates and equispaced. They are equispaced. It indicates that the source is somewhere, and this is the feed lines, and this is the uniform electric field. Electric field everywhere it's same. Let's take a dipole of dipole moment 12. This is suppose a dipole consisting of two charges, that is minus q and plus q, and the distance between them is 12. We know, suppose this is the center of the dipole, then the distance between the two dipole is 12, and let this dipole moment p vector, and the direction of dipole is always from minus q to plus q, minus to plus. So let a dipole moment p vector makes an angle theta with the uniform external electric field. Suppose it makes an angle theta with the direction of the electric field. So, and this is the perpendicular distance between them. Suppose this is A, this is B, this is C. So AB is the perpendicular distance between them, and we have to calculate potential energy. Torque on the dipole tau is equal to PE sin theta. If the dipole is rotated through a small angle d theta, suppose this is the direction of electric field, this is the direction of dipole moment, and the angle between them is theta. If this dipole is rotated through a small angle d theta, this angle is d theta, then work done in rotating the dipole from orientation theta 0 to then work done by the external torque is dw, small work done. So dw is equal to tau into d theta, and tau is equal to pe sin theta into d theta. So this is the small work done in rotating the dipole with the small angle d theta. So total work done will be integration. If we integrate both sides, then total work done w is equal to integration of dw, that is theta 0 to theta pe sin theta d theta. So it will be, let's pe, and the integration of sin theta is minus cos theta from theta 0 to theta. This is the initial orientation, and this is the final orientation. This work is stored as potential energy of the dipole. If the initial direction of the dipole, that is theta 0, if the initial direction of the dipole is perpendicular to the field, then theta 0 is equal to 90 degree, and final orientation is theta. So W is equal to minus PE cos theta from theta 0 to theta, and we can write it minus PE cos theta minus cos theta 0, that will be minus PE cos theta, final orientation is theta, and initial orientation is suppose 90 degree, that is cos 90, So it will be minus PE cos theta. So potential energy U, that is the work done, that is minus PE cos theta, or you can write it minus P vector dot E vector, because work is a scalar quantity. And so potential energy is also a scalar quantity and its unit is joule. Thank you.